this is the breadboard on which I will build the core system, and here are the key components. The 6502 from Western Design Center, and then we have two 32K SRAMs and some logic. Well, I seem to manage to pick 4 different logic families for the 4 different chips. Well, that is what I had in my box right now. So this is going on to this board. Unlike these Euroboards, they are pretty handy when you do some experimentation, and they measure 100 millimeters by 160 millimeters. They have 38 copper strips in this direction, and the spacing between the holes in either direction is 2.54 millimeters. And this I will use as the format for the expansion boards later on. And I can show you a little sneak preview what will happen later on. This is a part of the 3D printed design, and these are PCB guides, and the expansion board will go in like this and attach a very simple connector to the backplane board like this. But for now we will use them for user interface boards and build them with this component side up and solder on this side. Let's start with the status board. It will need 2 switches for NMI and IRQ, and LEDs for NMI and IRQ, and for sync and for the clock. Now we have some logic and some transistors and a bunch of resistors to make this thing work. So let's solder this thing. So here's the finished thing. We have the interrupt request control here, and interrupt LED, NMI LED and switch, and there's the sync or fetch instruction LED, and then the inverted clock here. And here's the connector to connect it to the rest of the board. Let's do the CPU control board. Okay, so this is most of the components for the CPU control board. Here we have the reset button, then we have the throttle, the CPU control potentiometer, the CPU speed control potentiometer, then we have the 3-way gear lever, that is low speed, middle speed and high speed, and then this will be the Alt run switch, and over here we'll have 2 more switches, one for instruction stepping, and I will place cycle stepping here and instruction stepping here with a different cap, a green cap on this one to separate them from the red reset button. Then we have some logic over here with this, the flip-flop and the other logic that we need, and some connectors, a couple of resistors and some capacitors to solder this thing ready. So this is the fixed or ready CPU control board, and it went pretty well. It was a little bit tricky with some of the resistors and capacitors to make actually the right values. As I mentioned previously, it is hard to get the 2 orders of magnitude range of a signal turn or a 270-degree turn potentiometer. But otherwise, I'm pretty happy with it. The only thing I regret is choosing these buttons. They don't have the tactile feedback as I would like. I would like to have this click feedback when you press them, and these are a little bit swampy or soft. So let's move on. Next is the memory access board. So this is the memory access board. We have the 2 LEDs indicating the read operation and the write operation. And these switches are 3-way switches which bounce back from the most extreme positions and stay in the neutral. So this will be read operation and read next operation, and this will be the corresponding for write operation and write next operation. Then we will have some connectors, some logic, and a Schmidt trigger. Did you know that this was invented already in 1936? It was Otto Schmidt, an American bioengineer or a bioelectrical engineer, who invented this by studying the neurons in squids. Anyway, it has ended up now on this desk as the 74HC4T. So this is the finished memory access board with a read and write switch and a mail connector, which I changed on all other boards as well, so everything is now mail connector. And I made a slight mistake when I cut this board into shape. I made it too small, so I had to add this, and then there's a joint over here which I tried to glue together on this side and to solder together on this side. But it kind of works as it is. I won't redo this. This is just iteration 1 and that's proof of concept. So now it's time for the address board. Well, the address board is so large that we have to use 2 different boards to do this. There will be a lower 8 bits here and a higher 8 bits here. There will be 8 switches, 8 LEDs and 8 transistors. We will have the connector over here for the address bits coming in here, and another connector over here. And we will have another connector here which brings in the LSW and ink signals from the memory access board. And then, if you remember the design, we had adders and output registers, and there will be a ripple signal going from the lower 8 bits to the higher 8 bits. So down here a ripple signal will come in addition to the LSW and ink signals that needs to go to both of the boards. So let's try to solder these together. So this is the 2 finished address boards. These are representing the lower 8 bits, and these are representing the higher 8 bits. The lower 8 bits plus VCC and ground comes in here, and the 8 bits, the 8 most significant bits are coming in here. And this is propagating the loads LSW and ink signals, and this is propagating the ripple signal going over. And you can see that while I did this one first, I learned that the output register shouldn't be placed here. I should have taken advantage of the strip construction at the bottom and placed it over here so that I can feed the signals nice and fit it nicely and attach them in a orthogonal manner in both ways. But both of them work, and let's have a look at the data board. So now this is the data board, and that means that the final user interface board is ready. As you can see, I got lazier and lazier, and I didn't bother to put up the empty board first and place all the components. But since this was it was very similar to the address board, I did this straight away. And I didn't mention it on the address board, but you can see here that I actually placed them in groups of 3, and that is inspired from the Altair 8080, which has an octal representation, or it's thought to be an easy way to see 3 binary digits 0 to 7 in an easy way, or at least easier than grouping them 4 and 4. So I think that I would try out to see how this triple configuration actually works out, and see if I will keep that iteration 2 or not. Otherwise, this works just as the address board. The big difference is that we don't have an 8-bit register to actually drive the bus. We just have a normal buffer, because either we are just displaying the data bus or we are displaying and driving the data bus. And here we have a similar connector as on the address bus. So now it's time to hook everything up and see how this complete construction works. So now everything is tied together and it seems to be working. So let me go through this really quickly. Over here we have the status board. Here's the clock, here's the instruction fetch, and this one we will take a look at. Here's the data board, and the address board, and the memory access board, and the CPU control board. And this is another board that I had to add because I made a mistake in the clock levels. I had to invert it. Okay, so let's power it up. Now the system is completely uninitialized, so let's take a route through the reset sequence. So now just the CPU is resetted. The memories just contain garbage. It doesn't have any defined values. But let's step through the reset sequence. So I will use the clock stepping here, and I'll press it once and twice, and the second time I press it, the instruction fetch lights up. But that doesn't mean that we actually fetch an instruction. It is just a part of the reset sequence. I will have to step it a couple of steps more before something interesting happens. And everything that happens up to now, and press number 8, is completely random. It doesn't seem to be have any significant values whatsoever. It changes every time the CPU is reset. 3, 4, 5, 6, 7. Here on number 7 we have now come to the position where we have F. Well, this is the address board and everything is lit. So this is F, and this is F, and this is F, and this is C, so FFFC, which is the lower 8 bits of the reset vector. It fetches that value, and the next cycle it fetches the most significant bit of the reset value at FFFD, and then we have the starting position. So at the next point we end up at the starting position, and it tries to fetch the instruction, and the instruction LED is lit up. But this means that this one lights up twice during the reset sequence. First it lights up at clock number 2, and then at the first real instruction. So that means we should be able to use the instruction step to pass through most of the reset sequence. So if I press that one twice, I should end up in the same position. So I've now set up the clock frequency at a pretty low frequency. So if I start to run this, you will see the clock tick at a relatively low rate, so you can visualize how the instruction stepping is working. So if I turn this on, we can see that the clocking goes on and it executes some random stuff in the processor, but every now and then it fetches a new instruction. But let's reset this and then do one instruction step. Now we are at cycle 2 in the reset instruction sequence, and then do another one. It steps through the rest of them, and now we ended up at the proper start address if the contents of FFFC and FFFD were to be proper, or if there were some valid values there. So that is the instruction step sequence.
This was all for this episode. In the next episode we will create a short assembly program, translate into object code and enter it into memory, and finally execute this program. See you next time!